Okay, for this last section of chapter 4, we are going to talk about optimization. And you'll see optimization is not a lot to it math-wise. Sometimes we just have to kind of work on making sure we understand the concept and we get all of that here. So I'll make sure to explain all of this here today. So we're going to build off of, again, everything we've learned so far. In this particular case, a couple ideas here. Just remember, and I'll draw a kind of a picture to show you what's going on here. We may have a graph that represents profit like we've done before. And the goal always is where is profit maximum? Where is the highest? We want to know where it's the maximum. Just like in other cases, there may be a graph like this, and this may be cost, and we want to say, well, where is cost going to be the lowest? Any kind of function, whether we're looking for a min or a max, don't forget, what's special about a min and a max is it has a slope of a tangent line equal to 0. So essentially our process is going to be, we're going to take a derivative of any function that we're trying to get the max or the min of. We take the derivative, we set it equal to 0, and when you solve for 0, you're finding that 0 slope, you're finding the x value or the t value or whatever, where you get this max or min. And that's our basic concept. Doesn't matter what it is, any kind of a variable measurement, if you set it, take a derivative, you set it equal to 0, you're going to get a max. So the first example, we're going to start kind of basic here. What are the dimensions of a rectangle with area 225 square meters that has the least perimeter? So let me just give you a couple of examples here. Okay, so we might have one that might be, let's say, 100. It's a rectangle, and let's just call this 12 and a half, 12 and a half. Okay, we can have another rectangle that might look like this, and don't believe these are just scale. I'm just kind of showing you an example. So we could have 75, 75, 37.5, 37.5. I think that adds up. Point is, in both of these, let me go back here. Start over. Sorry about that. I'm going perimeter when I was supposed to be doing area. One more time. So what they give us is not the perimeter. We're trying to maximize or minimize, in this case, the perimeter. So let me go back to this. They told us the area is 225. Okay, so a couple options there. We could have a rectangle. Remember, area is length times width. So there could be an area where it's 15 by 15. That's going to give me a 225 square meter area. Then if I finish this out, it's got an area of 225 and it's got a perimeter of 60 when you add all these up. Okay, then I can do something like this. Will be a little different. Let's say it's a 22.5 and a 10. Again, when you multiply the length times the width, you're going to get a 225, but my perimeter, 22.5 for that side, 10 for that side, we get a 45 plus a 20, we get a 65. Oops. So you see what I'm talking about, where these are the same, that's the parameter they tell us, but we're trying to find the minimum perimeter. So this one is better than this other one, but is that the best one? And that's the case of, well, we can just keep plugging in numbers all day, but that's going to take a while. The calculus, the derivative specifically, is going to tell us what the answer is to this one. Okay, so if you kind of break this down, kind of see where we're going on this one. We know the area formula is length times width, which is our 225. We know the perimeter is going to be the formula 2L plus 2W. Remember, that's adding one of the lengths, another length, one W, and another W, another width. That's where they get the 2L plus the 2W. So here's what we're going to do. The idea, the thing that we're trying to minimize, remember, is that we're trying to find the minimum perimeter. So what you need is you need an equation that has P. Ideally, we want it to be one variable. Now, as you get advanced, if you take a Calc 2 class, you're going to get double, triple variable problems with derivatives. But for now, we're going to try to stick with our single variable. So we have this formula right here. Okay, P equals 2L plus 2W. The problem is we have what do we have? We have too many variables. We have two variables. So we use this fact, the one they gave us when they told us the area, L times W is 225. They're solving for L, you could solve for W. You just solve for one of the variables. And you see this 225, we're going to replace the L with that. So that's what's going to happen in the next step. See that L, it was 2L plus 2W. We replace the L. We're just doing a straight substitution. Replace the L with a 225 over W. So now my equation for perimeter is 2 times 225 over W plus 2W. All this became that. And then they clean it up to be 450 over W plus 2W. So that's my perimeter equation right here. And what's nice about it is, like I said a second ago, it's in 2 variables. So that's the key that we're looking, or sorry, it's in 1 variable. That's what we're trying to get, is a single variable perimeter just equals 1 variable, and that's what we have. Okay, so now is where we go take the derivative. So see this thing, I wrote the derivative on the bottom. We're going to take the derivative of this. That's my P prime. So you know how to do this. Remember, that's 450 W to the negative 1. So I multiply the negative 1, drop the power by 1, it's W to the negative 2. That's how I get this. And of course, the derivative of 2W is just 2. So this right here is the first derivative. And then what they did right here, just so you know, they got a common denominator and combined the tops. So either of these are fine. But what matters is what we do next. We let that whole thing equal 0. So 0 equals, and they use the second one, the 2W squared minus 450 over W squared, and they solve to find the critical numbers. So when you solve for W, you have all these places right here, okay? All these are critical. Just so that we're all clear, remember when you have this equation right here? We've talked about this a number of times. You only have to let the numerator equal to 0, because that's the only time a fraction is 0 is when the numerator is equal to 0. So I could factor out a 2 and, I'm sorry, W squared minus 225. I can factor this and I get W minus 15, W plus 15. And basically, when you solve it, you get the numbers 15 and negative 15. Okay? So now we have to go back and think about what this is. Now, notice they circle 3 numbers as partition numbers. Well, the reason there's 3 partition numbers, by the way, is because 0 doesn't equal in the domain. That's why they put that there. Okay? But it's even less that we don't have to do any more than this. I'll kind of jump to it and say, well, W equals 15 is the only number that we count. Remember what W stands for. It's a width. It's a length of a rectangle. Sorry, it's a width of a rectangle. You can't have negative lengths, at least for now. A 0 length isn't going to help us, so we use the one that works, the 15. And what that tells us is when W is 15, that's going to give us the smallest perimeter, the minimum perimeter. So that's our only critical number. You don't even have to test for the concavity. If you get one number, that's going to be the answer. But you can, and they did the second derivative. They checked concavity and all that. But the least perimeter, all that matters is when the width is 15. Now, don't forget, sometimes they ask you, what was the length? What was the width? If they ask for the width, we have it. It's 15. If they ask for the length, we have to go back to the original equation and say, well, I know that the area was 225. Therefore, length times width equals 225. You plug in this 15 right here to the W, and it won't make a difference, but now L is also 15. So if they ask for the dimensions, make sure you tell them 15 by 15. If they ask for the length of the width, the answer is 15, and that's it right there. So in this case, I think they did want the dimensions. So there it is right there. The square side, 15 meters is the rectangle having the least perimeter with the area of 225. So that's, like I said, that's the goal on every problem. Literally, you make an equation. Sometimes you got to manipulate the equation and change things around. But once you get the equation, now you have to go and figure out what's the derivative, set it equal to 0, and then you'll have your minimum or your maximum. And the good news, like I said, is don't worry, well, is that a min or a max? Usually, if you only have one value, it's going to be the one that we're talking about, the answer to the problem. Okay, so let's look at this one. Homeowner has $320 to spend on building a fence around a rectangular garden. Okay, so on all of these, I recommend drawing a picture, but you don't have to. But you'll see what's going to show. They're going to show this in a second. Just realize what they're saying. Building a fence around a rectangular garden, and where we at here? Okay, so this is what's going on here. Let's see here. Oh yeah, they're giving more details. 3 sides of the fence will be constructed with wire fencing at a cost of $2 per linear foot. So $2 per foot length of fence. The 4th side will be constructed with wood fencing at a cost of $6. So this is sort of the rundown. Wood, $6 a foot, $2 a foot for this wire fencing right here. All right. Now they want you to find the dimensions and with the area of the largest garden that can be enclosed. Okay, so when they say largest enclosed garden, they're looking for the biggest area. Now remember how this works. If you had 10 feet by 10 feet by 10 feet by 10 feet, okay, $2 per foot, that's 20 here, 20 here, 20 here, and this would be 60. That would give us what, $120. So the idea is that we have to spend $320, and we want to make the biggest possible area here. Now, of course, as these get longer and longer, it's going to cost you more, so you have to be careful too, because as you make this side longer, it makes this one longer, but it costs $6. So we got to figure out what to do here. So you notice the first thing is they're assigning variables. Let's call this X and this Y. All right? So now, there's your X and your Y, and the area of the garden. If you're trying to maximize the area, which the question is asking, you need an area formula. Don't worry if it has a bunch of variables. Let's just get a formula right there. So we have area equals X times Y. That's our base formula. Now we have to try to figure out how this fencing cost works. So look and see how they did this. Notice the cost is going to be 2 times Y, because remember this is Y over here. So that's this side, $2 a foot. That's why it's 2 times Y. So however many feet Y is, you take 2 times it, and that's the cost. Just like 2 times this X, 2 times this Y, and of course this side is also X, but it's $6 a foot, so that's 6X. So your cost formula is 8X plus 4Y. Well, we know the cost already is going to be $320, so I'm going to let that equal to 320. There's my formula. So as long as you have, if you go back, the area had 2 variables. Well, as long as you can make a formula with both those variables, you can then do the same process of substituting and then break down that area formula. So they're going to solve for Y. So get the Y by itself, move the 8X over to become a negative 8X. We'll divide both sides by 4, and we get this equation, Y equals 80 minus 2X. So keep this in mind. Y equals 80 minus 2X. That means anywhere that you see a Y, you can substitute it, just like you did in algebra. So back to our area equation. We need the area equation because remember, that's what we're trying to maximize. So this area equals X times Y. I'm going to replace the Y with 80 minus 2X. So again, here's what we know. Here's the formula. In place of this Y becomes the 80 minus 2X. So my new area equation, they didn't actually show it right, but here's what it is. Area equals 80X minus 2X squared. That is my formula for area. All right, based on what they gave us, that $320 budget. All right, so now a couple other facts. If you can read that, X and Y represent the dimensions of the rectangle, therefore they have to be non-negative. All right, now non-negative can have a 0. Technically you can have a 0, but you guys know this. If you have a rectangle and one of the sides is 0, there is no rectangle. All you have is a line, like a long fence. So we'll assume it's got to be bigger than 0, but X is 0 or bigger, Y is less than 0. This is a typo right here. They're both supposed to be greater than 0. So a couple things here. We're going to move on here. We don't really care about all that. This is what we're looking at. Area equals 80X minus 2X squared that we talked about. All right, that's what we're going to maximize. That right there. We want to maximize this. So I'm going to take the derivative of the A. And they say critical numbers, the derivative is what we're looking for though. 80 minus 4X, and we're going to set that equal to 0, and you get X equals 20. What that tells me is when X is 20, go back to this picture, that X value of 20 is going to give us the best area possible based on our $320 to spend that we have to spend. Okay, so we know 20 is the number. Now, they brought up that x is between 0 and 40. That's what the stuff was that I skipped. It's not 100% necessary. I mean, it's good to know, be able to come up with this, but this is just defining parameters of x. We can't get x anything bigger than 40, all right? Because if you make it bigger than 40, it's essentially not going to be a possible rectangle. Go back to my rectangle here. If x is bigger than 40, what's going to happen is 40 times 2 is 80. 40 times 6 is 240. That's going to be your $320 right there. So anything bigger than x, it could be a real long rectangle, but anything bigger than x being 40, we're going to overspend our budget right there. So that's all. That's how they got all this. Not the most important thing. The 20 is what matters. So that's going to be what we care about. And like I said, you don't have to go through all of this right here. All we have to figure out is which one gives us our best. That's going to be our 20. So depending on what they ask for, if they ask for, well, what is the area of that? We go back and we plug that in. Okay, where's that formula? Remember this area formula right here? This 80x minus 2x squared. Since we know 20 is the winner, plug in 20 here, plug in 20 here, and that's how we got the area of 800. Okay? And then from there, how did they get the 40? Well, go back to this again. Where's that equation with x and y? Sorry, right here. Y equals 80 minus 2x. Well, once we know x is 20, we can replace that with 20, and we get 80 minus 40. That's where the 40 came from. So that's how they're getting those other dimensions, the side lengths. So the only thing you got to worry about here, and I don't say the only thing, but one of the things you have to worry about is make sure you answer the question. Whatever the question was, just make sure that you're exactly answering what they have asked for. Okay, so now they have a little summary procedure here, and I'm going to do maybe one more example. I'm not going to do all the PowerPoints because you can kind of go through these because they're all pretty much the same, just as a reference, but I want to get into the homework problems that you have here. So we're going to talk now about the strategy, and this is just the summary of how to do these problems. Okay, so here's what we're going to do here. Introduce the variables, and the big thing here, like I said, I'll let you read it and kind of go through it here. Main part is you need to create an equation of the thing you're trying to maximize. So if they or minimize, if they're trying to tell you to max or min area, you need an equation that says area equals this. If you're trying to maximize volume, you're going to say V equals this. If you want to minimize cost, C equals that. You have to create an equation with the variable that you're trying to take the max or the min of. Once you get there, then you need to try to break it down to get it down to one variable. Okay, you can't have an x and a y. You got to get down to one variable. Then at that point, take the derivative, find those critical numbers, and then whatever those critical numbers are, there's usually going to be one of them. That's your max or your min. Okay, if you need to go further and find intervals where they're increasing, decreasing, or concavity to confirm it's a max and a min, by all means. But I'll give you that hint. Like I said, almost everything's going to have one critical point, one special number for the zero derivative. That's your answer. Okay, so in it was that same homeowner problem here. Say they decide that 800 square feet for the garden is too small and decides to increase the area to 1,250 feet. What's the minimum cost of building a fence that will enclose a garden with an area of 1,250 feet? What are the dimensions of this garden? Okay, so the cost thing, assuming it's going to be the same here, I want to make sure 1,250 square feet. Okay. Okay, the $2 per fence and the $6, that part's staying the same. So that's how they get this right here. This is the same equation of the cost earlier. Remember, three sides that were there was a side that was X that was 2 feet and one was 6 feet. You add them up, that's where you get the 8X. The Y sides were both 2 feet, $2 a foot. That's why it's 4Y. So that's our cost right there. And now we have to figure out how to get this 1,250. So remember, area is 1,250. That's X times Y. All right? We want to minimize the cost. That's the question. So go back and read the problem again. What's the minimum cost of building a fence that will enclose a garden with an area of 1,250 square feet? Now in this one, we are going to have to do a little bit of extra steps here, but watch what we do. So we know they have to be greater than 0, and they can't be zeros because it's a positive area. So we solve for a letter just like we did before. They solve for y and get 1250 over x. We're going to use that and go back here. We're going to plug that into the cost equation. So see this one on the top right, 8x plus 4y. Replace the y that we just solved for with 1250 over x, and then it simplifies to be 8x plus 5,000 over x. And that's what we're going to try to minimize. We're going to try to take that derivative right there. So you see the derivative right here. Let me stop and make sure you get this. Right here is what they took. Derivative of 8x is 8. This is 5,000x to the negative 1. So when you take the derivative, you get a negative 5,000x to the negative 2, hence this answer. All right, we set it equal to 0. That's always the immediate step. Get your derivative, set it equal to 0, and now solve for x. Well, they move this over to the right, multiply both sides by x squared, divide by the 8, and we end up ultimately getting, x equals 25. X squared is 625, so x equals 25. And now, the thing they did right here again, this goes right to the second derivative. Right here. Take the second derivative, you get 10,000 over x cubed. And all this is to see what's the sign when you plug in the 25, the one we just found. Remember we did this the last section. We found a critical point in 25. Is that our max or min? Let's find the concavity at that point. So we plug in 25, that number, to the second derivative. It's greater than 0, therefore it's concave up. Therefore this 25 should be a minimum. And that's how we know from that second derivative here. All right, so it must be a local minimum. And now they say it's an absolute minimum. Well, how do we know is, well, if you go back to this equation right here, the actual cost equation, you can actually look at, well, let's plug in 0. That doesn't work. You can plug in some other numbers. You can see what's the limit as you approach 0. You can see what's the limit as you approach infinity, just in case it keeps going down. But really the only answer that matters is that 25 that you got right there. Okay, so you can plug that into the cost function. This one right here, the top. You plug in 25 to this, and that's where they got the cost of $400. All right, you take the area equation. Since you know the x is 25, you solve for y, and you get y is 50. That's how you know the dimensions of your fence. All right, to make a 1,250 square foot garden, it's going to cost you at minimum. The smallest cost you can make is $400, and the dimensions are going to be 25 by 50 feet. And they even clarified the 25 foot is going to be the wood fencing side. Okay, so let me jump into some of these homework problems. Like I said, we're about halfway through the slides. There's about 3 or 4 more examples, and I highly recommend looking at them if you want. They're just, again, to show you more of these, but like I said, I don't want to make it sound like it's easier than it is, but it really is a few basic steps. You're putting a lot of things together, but the steps are: make an equation of the thing you're trying to get a max and a min of, take the derivative, set it equal to 0, and you have your answer. Okay, so let's look at our assignment here. As you recall, there weren't a whole lot for section 4.6. If I can get it to pull up here. Okay, so we're on this homework right here. Let's look at that one, and you see we've only got a handful of problems. Let's look at number 35 and see what this is all about. Okay, express the given quantity function f of x as one variable x, the product of 2 numbers x and y whose sum is 14. Okay, so let's kind of talk about this. We want to express this given quantity, and it's not easy to see, but this is what they're asking for right here. All right, what we should have is the product of 2 numbers. That means we're multiplying. Okay, that's it right there normally. How do you write the product of 2 numbers x, y? It's x times y. But they want you to express this as one variable. Well, this is where the second part comes in. When the sum is 14, then you know x plus y is 14. We want to express this right here as only the variable x. Basically, we need to get rid of y. Well, how do you get rid of y? You find another equation that has y. You solve for that y, and that's what you replace in here. Okay? And then I can make that 14x minus x squared. Either way, that's going to be my function that I'm going to put in right here. 14x minus x squared. And there's our expression. That's the product of two numbers where the sum is 14. So we incorporated the sum, we solved it, and that went into the product. And then we made this as a variable, one variable equation. Okay, so let's look at number 39. Okay, find two positive numbers whose product is 85 and whose sum is a minimum. So I'm going to focus on the minimum part right there. Okay, so they want the sum to be a minimum. That's our goal right there. So remember what I said. We need to find an equation for the sum. Doesn't matter what the equation is, it just has to be an equation of a sum. Well, we have two positive integers. Let's call them x and y to start off. Okay? Just x and y. Well, therefore, the sum is going to be x plus y. That's our equation of sum. The thing we're trying to find the minimum of, we make an equation. Now, we want to get it down to one variable. That's the next goal. Well, we have to find some other information so that we can get rid of one of the x and the y's. The only way to get rid of either the x or the y is I need another equation that has x and y in it, and that's where the second part comes in here. They tell you, oh, sorry, that part right there. The product is 85. So that's my second equation of, let's get rid of this. Okay, the product is 85. That means if you multiply x and y, you get an 85. So I have this equation that I'm trying to take the derivative of, the minimum sum. I need to get rid of one of the variables. I'm going to use this right here to get rid of one of the variables. So it doesn't matter which one. Solve for any one of them. Okay? Y equals 85 over x. I'm going to use that right there. So my sum is now going to be x plus 85 over x. And that is the thing that I need to take the derivative of. S equals x plus 85x to the negative 1. And notice I put it in that form that I wrote as 85x negative 1 because I know I'm taking the derivative next, so let's get it in derivative form. So S prime is 1 minus 85x to the negative 2. So S prime equals 1 minus 85 over x squared. Then the next step, set the derivative equal to 0 and solve for x squared, or solve for x. So now I get 85 over x squared equals 1. Everyone see what I did here? Take this, and I move it over to the left. That's why it becomes a positive. So 85 equals x squared. X equals the square root of 85. And they want you to type an exact answer with the radicals. And this is important, not a decimal. That would be your inclination for some of you. Let's go plug in the square root of 85 and get a decimal. But when they say exact answer, that means don't give a decimal. We want to see a perfect square root. Now let's keep in mind what's going on here. Remember my two numbers? They're x and y. We found that root 85. Now notice, I didn't write this, but when you take a square root, you're supposed to have a plus or minus. But because they told us these are positive numbers, I only care about the root 85. That's the first number right there. Now we have to figure out what the second number is, and it's not so bad because go back over to here. We know x times y is 85. So if I replace x with root 85 and divide both sides by root 85, I'm going to get another root 85 right here. So those are my two numbers. And this is important because a lot of people would just say, okay, well, the answer is root 85 and be done. And I'm going to do that just to show you. They're going to tell you wrong. What's going on? It's because they want you to type both numbers. And even though you know these are exactly the same, they're not always the same. Sometimes they are going to be different. So you need to put them both in there, and that's what we did here, and that's how we have our answer. Okay? So pause that if you need to look it over. I know I've got work everywhere. And when you're ready, unpause. And let's look at number 43. Okay, a candy box is made from a piece of cardboard that measures 27 by 15 inches. Squares of equal size will be cut out of each corner. The sides will then be folded up to form the rectangular box. Okay, so if you've ever seen this before, if you ever cut the cardboard and play with it, you can kind of get the idea here. Here's a rectangular box. What we're doing is we're cutting off square corners. Okay, so essentially these are going to be gone. Gone, gone, gone. And then what we're left with, if I can draw this, kind of this cross-shaped, and these dotted lines are where I'm going to fold the box, the lid, the flaps up, and what I end up getting is, see if I can do this here, you're going to get a box, and my three-dimensionals are not going to be perfect, but box that kind of looks like this with an open top. Okay, that's what it's kind of like a shoebox without a lid. So the question they have is, we know this cardboard box is 27 by 15, and the question is, what size of square should be cut from each corner to obtain maximum volume? So we know I need an equation right there. Now, where's my variable? Well, I'll tell you where it is. Remember, they're cutting squares here. So maybe we cut a 1 by 1 square. And then we have to cut a 1 by 1 everywhere because otherwise it won't make a perfect box. So we can do 1 by 1. We can do 2 by 2, 3 by 3, 4 by 4, whatever it is. I don't know what it is, but what I do know is it's a square, and we can then use that information to figure out what the volume is. Okay, so now I'm going to do this a little bit unconventional. This is not how you need to do the problem, but let's just pretend. Let's pretend we cut off a little 2 by 2 square off of each end. Now, when I fold this box, let's just look at this right here. This is going to be the length, this is going to be the width, and the height will be right here. Okay, now if you look at the flaps, the height is actually how far it's sticking out as that goes up. So to find the volume, it's length times width times height. That's the thing that we have to maximize. Okay, that's our formula for the volume of any kind of a rectangular box type object. So looking at my picture, let's say we did cut these 2 by 2 corners off of every edge. Well, see this 27 goes from here to here. If I cut 2 off here and I cut 2 off here, I've essentially subtracted 4, so this length is going to be 23. Same with the width. If it's 15 and I cut off 2 and 2, I'm cutting off 4, it's going to be 11. And then my height, ironically, it is how big the square was. It was going to be a 2. So the volume of this box will be 23 times 11 times 2, and whatever that turns out to be here, get my calculator again to be sure, 23 times 11 times 2. This volume gives me 506 cubic inches. Is that what they said here? Yeah, inches. Okay, that's one volume. That's when we cut out the 2-inch corners. And you see I can do this again with 3. And I can do the same process. But we can't do this with all the numbers. It's going to take forever. So the idea is, if I'm looking for the maximum volume, I want to try to create an equation that I can take a derivative. Now remember the key, we need to get down to one variable. One variable, and right now I've got 3. I have L, W, and H. So how do we do that? Well, kind of look at, I'll draw kind of a bigger picture here. What I'm saying is, I don't know how much we're going to cut out. Is it a 2 by 2, a 3 by 3, a 4 by 4? I don't know. So let's say the little squares we cut are x's. So it's x by x. X could be 2, it could be 3, it could be 18. I don't know. It's going to be something. So that's going to be the x right there. Now, since this whole thing is 27, we need to come up with this length. Let's do that pink again right here, because that's going to be my length. Well, remember how we did it before? We took the 27, we minus the 2, we minus the 2 again. Well, we don't know what the number is, but to get that length, I'm going to take the 27, I'm going to minus the x, and I'm minus x again. Basically, my length is going to be 27 minus x squared. Or sorry, 2x. Not x squared, 2x. And on the same hand, this width right here is going to be 15, because that's how long this was. 15, we said, yeah? It's going to be 15 minus the same 2x, because we're removing x and removing an x. And the last part is our height is just simply whatever x is. Whatever size we cut out of the corners, that's going to be x. So now, after all that, I can take this equation right here. Length times width times height. And, excuse me, I'm going to replace it with all these values we found. L is going to be 27 minus 2x. W is going to be 15 minus 2x. And the height is going to be just plain x. So I need to make this is my volume equation. Now here's the good part. It's one variable, exactly like we're shooting for. I just now want to get it ready to do my derivative. So in order to do that, I got to multiply everything out. First step, let's take that 27 and multiply it. Let's go down here. I'm going to FOIL out. So 27 times 15. If you can do it in your head, good. If not, you better use a calculator. We get a 405. Now outside we get a minus 54x, and inside we have a minus 30x, and the last term is a positive 4x squared. We then are going to take that, and I'm going to erase some stuff up top here since we've already kind of established all of this. I'm going to get my clean, simplified derivative up here on the top right of the screen. So everything I just did was from foiling, and now I still have that last x that's multiplied on the back end. This x right here. So that has to distribute through everything that I just found. So my volume is going to be 405x. And then this, keep in mind, you can add those two terms. That looks like it's an negative 84x. So when I multiply the x, it's a negative 484x squared. Remember, the x is distributing to everybody inside. And my last term is a positive 4x cubed. This is the thing that we are trying to maximize. Remember the goal. Maximize the volume of the box. First step, find an equation for the volume. Well, I got it right here. See on the bottom right, volume equals LWH. Then we use the other information, because something else has to tell you some dimension restrictions or facts. We know it's a 15 by 27. We know we're cutting out a corner. So from all of this, we converted it to this equation up top. And now I'm ready to take the derivative. And we have this one right here. So now we have our derivative. Our goal is set it equal to 0. Now I'm going to rewrite it in the order that I'm used to, descending order. And we want to somehow see if I can factor this and find out what these maximum and minimums are. Okay? So remember when you do this here, you got to somehow factor it. Now, if this is a 168, based on what I'm seeing, I think we can factor out a 3. I can divide everybody by 3. So look for a common number. And like I said, I'm seeing that we can divide everybody by 3. And that's not a big deal when you have an equation equal to 0, because the left side stays as 0. But this makes our lives a whole lot better in the terms of, well, we got some smaller numbers to deal with here. Okay, so now I'm going to try to see if I can factor this, and I don't know the answer right now. I'm just going to mess around. Let's go with a 2x and see how that works. But remember, I'm factoring. I got to think of two numbers that multiply to be 4x squared. Let's just try this. Two numbers that multiply to be 135. Well, since this is positive, remember, these numbers have to be both positive or both negative, and we need a negative in the middle, so it's got to be a negative right there. Okay? And I'm thinking 35 times 3. I don't think that's going to work. I'm thinking 5 times 27. And that's going to be close, but I don't think it's going to work. We get negative 10 minus 54. We're close, but we're not getting to minus 56 inside. Let's try 6, 7, 8, 9, 10. I think 15 will work. That will give me 9? 15 times 9, I believe. Try to do this quickly in my head. I think that does work. Yeah, 15 times 9 is going to be minus 135. And when I FOIL it, though, I get minus 30x and minus 18x. Notice that gives me a minus 48x. Okay, so I'm not really getting that. And here's the thing I want to tell you with factoring. I always like to attempt factoring at first because if it works and you get a nice number, it saves you a lot of headache. Unfortunately, not always are you going to get lucky. You know, it might be 4x times x instead of the 2x times 2x, and that's probably what it is. But I don't know what the answer is. If I've been trying for a little bit, and this is where factoring can get frustrating. If you try it a few times and you don't get an answer, then I'm going to tell you, you know you can use your quadratic formula. Okay? Some of you will go to the quadratic formula right off the bat. That's fine because you know how long it's going to take. It's going to take the same amount of time no matter what problem it is for the most part, whereas factoring is kind of hit and miss. Sometimes factoring is faster than the quadratic formula. Sometimes it's longer. At least you're safe when you know what you're getting with something like this, you know, with the quadratic formula. So, okay, let's try this again. We have a 4x squared minus 56x plus 135. Remember, that's your A, your B, and your C. And that's what you're plugging into your formula here. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And yeah, like I said, it's going to be bigger numbers. It's going to take a little bit of work, but let's see what we end up getting here. And again, quadratic formula could produce big numbers, so don't be afraid to get your calculator out. 56 squared gives me a 3,136 minus 4 times A times C. So I'm going to take that 4 times the A, which is also 4, times the C, which is 135, and I get a 2160 inside. All of that is going to be over 2 times 4, which is an 8. Okay, so we're going to take that 3136, subtract off the 2166, and we get a 976. Notice I keep putting that 8 on the bottom. Don't neglect that. Okay, now sometimes we'll see 976 is a perfect square root, and it's not. Okay, so before I go any further, I want to go and look at that problem and make sure. Do they want decimals? And sure enough, see it, they want you to round to the nearest hundredth. So that tells us don't worry about trying to maintain this as a perfect root. Let's go ahead and get the decimal 31.24. Okay? Now, let's say I went one more decimal place. Let's just go to the thousandths for fun. It never hurts to go a little further, and then you can go and see what comes up after that. Okay. So now we have all of this. Let's not forget what it means when you have a square root. So I'm going to, again, start erasing some old stuff here. You can always rewind and look back in the video if you need to see these steps previous, but I want to try to keep everything up on the screen as best I can. So right now, what does it mean when you have a plus or minus? That means it's literally two different solutions, two different equations. One equation has that as a plus, one equation has that as a minus, and everything else in that equation should stay exactly the same. Don't touch anything else. So what does this mean? It means we have an x equals 56 plus 31.241 all over 8. And just to be safe, I'm going to go a little bit further because I know we're going to divide in a second. So let's just go, no, that should be fine. But when in doubt, like I was having a doubt, go a couple extra spots. So this is the first part, 56 plus the 31, or x equals 56 minus the 31.241. So you treat these as two separate equations to get two different answers. All right. So I'm going to take that 56 plus 31.241 and divide that by 8, and my answer is 10.91. Over here, I'm going to do the same thing. Take the 56. This time I'm subtracting the 31.241, and now I divide that by 8. And our second possible answer is 3.09. Okay, so now the whole goal of this, remember, was what size square are we going to cut out of the box to get the biggest volume? Well, the x, remember, that was the size of the square. So my two answers are these right here. It's going to be a 10.91 by a 10.91, or it's going to be also a 3.09 times by 3.09. And let's see what we get here on this one. Okay, now notice we have two answers, and I wish I'd left up the picture here. Keep this in mind. Let me go. I'm going to draw that picture again real quick. Remember, it was a 15 by 27. Here's 27, and here's the 15. So this is what we're cutting out, this x by x. So let's start with a small one. If I cut out a 3.09, I would do that from both parts. So I'd cut out a 3.09 from here and a 3.09 from the bottom, each corner. All right, so that's a little more than 6. Well, if this whole thing is 15, that's not a big deal because I'd still have this leftover bit inside. Okay, so this is good. Now I want to show you the other part. What happens if we went with a 10.91? Now I want you to look at how the picture works. If I cut a square that was 10.91, it would be like this. And then I'd have to cut another 10.91 from over here. We don't have a three-dimensional box. Okay? If you're cutting off two of these, remember how we're subtracting 2x? Here's the other way to look at it. Remember that width was 15 minus 2x? Well, if I plug in 10.91, I get a negative number. We can't use a 10.91. The only number we should be able to use is this 3.09. So they say a square with side length of 3.09 should work, and there's our answer right there. So it's got the procedure, but you still have to make sure you answer the question, and you have to stop and just kind of ask yourself, is this possible? Can this work? This can work. The other one cannot, but this is our answer right here. So if you're trying to make the biggest box that'll hold the biggest amount of stuff, if you have a 27 by 15 inch, cardboard, and like I said, we've done this before. You take an Amazon box, or you take any kind of a box, you're trying to wrap a present or store it for something. You cut these squares out, you put the flaps up, you get a box where you can hold stuff. Well, if this is my cardboard and I have to cut squares out, we actually know the precise measurement, almost 3.1 inches. You cut that off of every corner, and that's the biggest holding box you can have. There's our answer right there. Okay, so that's pretty much it. I think that was it for this chapter. I want to make sure we got all of our problems. See, that was number 43. I don't think there was a 47, was there? Yep, that was the last problem right there. So that's it for your homework. Yeah, let's get these up here. So yeah, we've pretty much done all the homework. There's not a lot for this section 4.6. The bulk of it is 4.5. So with these two, you should be good. Couple reminders. Remember, homework for this week, because next week is spring break. So your quiz is actually not due the Monday of spring break. It's due the Monday we get back. It's like there's a big 1 week pause. So no quiz due on Monday the, what date is that? The 11th. The quiz is going to be due on Monday the 18th. And then that's when we're going to start the next chapter. And the good news after spring break is it's only going to be one section. It's going to be a kind of a nice gradual get back into the swing of things chapter. So we'll work on that when we get back, and then we'll have just one section, one lecture next week, and then one section on the quiz. And then we'll be getting close to finishing up everything. So like always, if you have any questions, feel free to shoot me an email, and I'll help you out. And other than that, have a good spring break, and don't forget the quiz when you get back. Now, if you already did the quiz before, good for you. But if you leave or you're gone on vacation, whatever reason, make sure you do that quiz that Monday night before you get back. And I will, again, try to remind you guys on Monday just so you have that. All right. Have a good weekend. Have a good week. Take care.